So next talk is on coinductive proofs of regular expression equivalence in zero knowledge. And the talk is given by John.
Yes.
Please.
Thank you for the introduction. My name is John Kolesar, and today I'll be giving a presentation on the paper Coinductive Proofs of Regular Expression Equivalence in Zero Knowledge. We want to have private proofs about regexes because, for instance, we might want to verify a regex-based content filter that's part of some larger system. We might want to filter profanity or spam in messaging apps, or we might want to have a front end for a generative AI system that uses regexes to reject queries that contain specific terms. For instance, if we don't want users to ask sensitive questions about topics like voting, we could pass the user's message through a private filter regex that looks for the words vote and elect. If we get a match on one of those words, we reject the query instead of sending it forward to the rest of the system. Now, the developers of a filter like this would want to keep the filter private to hide potential vulnerabilities if they exist. But for legal reasons, that filter may be required to be at least as restrictive or permissive as some public specification. And an external auditor would need to confirm that. The standard way for that auditing to happen is for the developer simply to hand over the filter directly to the auditor, but that contradicts our goal of keeping the filter private. Fortunately, a better alternative is possible with some techniques from cryptography. With a zero-knowledge proof, the developers would be able to convince the auditor that the filter satisfies the spec without revealing exactly what the filter is. Instead of just giving the filter directly, the developer would provide an obfuscated proof certificate about the filter that doesn't show what the filter is, but provides evidence that it meets the spec. There are other use cases for private regex proofs as well. Network programs use regexes for packet filtering, and on the theoretical side, regex equivalence is a PSPACE-complete problem. So by targeting this, we're the first to target a PSPACE-complete problem in zero knowledge. More specifically, to address the problem, we introduced Crepe, which stands for Cryptographic Regex Equivalence Proof Engine. Crepe is a zero-knowledge protocol that lets us prove that two regexes are equivalent. In our setup for the protocol, the prover owns both of those regexes and generates an equivalence proof for them offline, and then sends an obfuscated version of that proof to the verifier, who validates that proof using a custom proof VM. For some background, a zero-knowledge protocol, or ZK protocol for short, is a cryptographic method of communication between two parties known as the prover and the verifier. The prover convinces the verifier that it knows some secret without revealing the evidence for the secret. The quintessential ZK example is the Coke-Pepsi taste test, where the prover has some secret knowledge about how to distinguish Coke and Pepsi by taste, and the verifier wants to confirm this. The verifier would fill a cup with either Coke or Pepsi secretly and ask the prover to say what it is. If the prover gives the wrong answer, the verifier knows the prover was lying. But if the prover gives the right answer, and they repeat this process enough times, the verifier eventually becomes convinced. Importantly, the verifier never learns how the prover is doing it, and that's the essence of zero-knowledge proofs. I should mention at this point that I'm using the word proof in two different senses. For our purposes, we want to provide a ZK proof about the existence of a logical proof. When we want to move into the domain of regex equivalences, the proof that we provide is a list of discrete steps where each step in that proof has pointers to the other steps that it uses as premises. And the prover and verifier iterate over this table of proof steps one by one, confirming that every individual step in the proof is valid. And we reveal information about these steps only selectively, so that the verifier can't see the values manipulated by those steps, but can see that the steps are valid. We have three main building blocks for our approach for Crepe. We have our new proof format for representing these proof certificates. We have a new algorithm for generating the proofs that we validate. And we also have a new proof validator for confirming that proofs are correct on the verifier's side. Let's talk about these one by one, starting with the new proof format. We base our proofs on an important observation from prior work, which is that if two regexes agree on the empty string and all of their corresponding derivatives are equal for the whole alphabet, those two regexes themselves must be equal. Now, what exactly are derivatives? Well, if P is a regular expression and C is a character, then the derivative of P with respect to C is the regex that represents the behavior of P after reading C from an input string. For instance, the derivative of AB or AC with respect to A is B or C. The derivative of BC with respect to A is the empty set because BC doesn't accept any strings that start with A. And the derivative of A star with respect to A is just A star because reading one A doesn't limit the number of further A's that we can read. Let's take a look at how we can use these derivatives in action to prove an equivalence between two regexes. Suppose that we want to prove that A star or A star is equivalent to A star. We have only one character for our alphabet, so we have two proof goals. We need to show that these regexes agree on the empty string, which is what this E function represents, and we also need to show that their derivatives with respect to A are equivalent. Both of these regexes accept the empty string, and that takes care of our first proof goal. And for the derivatives, we have A star or A star and A star. These two things aren't identical to each other, so we need to prove separately that they're equivalent. And to do that, we recurse, and we use the same proof strategy again on these new regexes. If we want to prove that A star or A star is equivalent to A star, we again need to show agreement on the empty string and derivative equivalence. They both accept the empty string, and their derivatives are A star or A star and A star. That means that if we want to finish the proof now, we need to show that A star or A star is equivalent to A star. But this is exactly how we started this current step, and that means that we've reached a cycle. This cycle is actually an important part of the proof. We haven't seen any counterexamples on this cycle since all the corresponding regexes have agreed on the empty string, and that means that further repetitions of this cycle won't yield any new counterexamples. And because our alphabet is only one character, the only way to keep exploring forward to see more potential counterexamples is to keep moving along this cycle. So that means we've exhausted the entire possible space of potential counterexamples, so there are no strings on which our two starting regexes can disagree, and that means that they're equivalent. And that's how we finish our proof by coinduction. And to express this kind of reasoning in a proof that we can validate in ZK, we create a custom calculus of logical rules for reasoning about these cyclic patterns in the derivatives of regexes. And you can see some example rules in this table. Now that we've talked about our proof format, let's talk about how we generate proofs in this format. We base our proof generation approach on this regex equivalence algorithm, which comes from prior work. We search the trees of two regexes' corresponding derivatives exhaustively until we find a counterexample or we hit a cycle on every branch. This algorithm is guaranteed to terminate because the derivatives of a regex must fall into a finite number of equivalence classes. That means we're guaranteed to hit a cycle on every branch eventually if there are no counterexamples. We can convert this equivalence checking algorithm into a proof generation algorithm by recording the execution trace of our derivative search and turning that trace into a proof tree and returning that tree as our output instead of just returning a Boolean result. Now let's talk about how we validate these proofs on the verifier's end. When we're validating a proof in ZK, we hide the values manipulated by each proof step to make different uses of the same proof rule indistinguishable from the verifier's perspective. We accomplish this using a standard cryptographic technique known as commitment. That means we map integers to elements of a special finite field such that recovering an integer from its commitment is not computationally feasible. You can think of it as working like a hash function in that regard. Also, when we're validating individual proof steps, we use multiplexing. That means we run multiple rule checking functions on each proof step, only one of which is for that step's real proof rule. And the verifier can't see which of those checkers is the real one, but can see that at least one of them succeeds for a step. And in our implementation, we group our proof rules into three categories for multiplexing, where the verifier can see the category of each step's rule, but not the specific rule within that category. Now let's move to talking about our evaluation for Crepe. We test both our proof generator and our ZK proof validator. To test the proof generator, we attempt to generate equivalence proofs for 7,353 equivalent regex pairs from Flash Regex, which is an older tool. Of those pairs, 72 hit our time limit of 10 minutes, but all the others succeed, and you can see the running times on this log scale. After we generate all these proofs, we select the largest ones to use as benchmarks for our ZK proof validator in the next step, along with some random samples from the rest of the collection. You can see the running time statistics for the two categories here. In general, the benchmarks that we selected are slower to run than the rest of the benchmarks because we chose the biggest ones according to multiple size metrics. The proof step count statistics follow a similar trend, where the benchmarks that we selected have more proof steps in general. To test our proof validator, we run our ZK proof validator on those proofs that we selected from the first part of our evaluation, and we use multiple different configuration options for it. We use our default settings with the 3 multiplexing categories that I mentioned before. We use no multiplexing, which means the only checker we run on a proof step is the real one. We use full multiplexing, which means we run all checkers on all steps. And we also run it in plain text, which means we disable all ZK operations. No multiplexing is faster than the default but less secure. Full multiplexing is slower and more secure. And plain text is faster by 3 orders of magnitude but provides absolutely no security. The median running time ratio of no multiplexing to the default is 0.74, and the median ratio of full multiplexing to the default is 3.42. That means that with our default settings, we can achieve realistic performance that's comparable to what we get with no multiplexing, while still getting significantly better security than what no multiplexing provides. To conclude now, I'll talk about some related work and potential directions for the future. There are other ZK protocols for validating logical proofs, but none of the older protocols target regex equivalence specifically. They target other formalisms. Also, there are older ZK protocols for reasoning about regexes not inside logical proofs, but they only check membership of individual strings in a regex and not regex equivalence. For some future work, we could improve Crepe by extending it to handle clean algebra with tests, and also features that are not allowed in pure regexes, like intersections and complements, and back references and look-ahead assertions. We could also move to handling other PSPACE-complete problems in ZK, like NFA equivalence, and of course, performance optimizations are always possible as well. To conclude, our contributions are that we create the first zero-knowledge protocol for validating regex equivalence proofs. We create the first practical ZK protocol designed to target a PSPACE-complete problem. And to support that protocol, we create a new custom calculus of proof rules for expressing proofs about regex equivalence, along with an algorithm that generates proofs in our format. If you want to discuss this with me further, you can reach me at this email address or at my website. I'm on the job market if you want to talk about that. So thank you for coming to my presentation. If you have any questions, I can take them now.
Questions?
Hello, thank you. Is there a particular design choice between using the derivatives and sort of induction type thing versus using like an automata normalization for your proofs? Like, is there a crucial part of that? Is there like an intentional crucial part there?
Yes, it is intentional. If we used proofs based on state machine conversion, we would need to provide evidence of the correctness of our translation of these starting regexes into state machines. And by using derivatives, we're avoiding that layer of indirection, since we're reasoning about regexes directly, so we never need to validate a conversion between 2 different formats.
Thanks for the talk. Do you think it could be applicable to omega regular expressions? This would be, for example, a good starting point for zero-knowledge model checking evidences.
What do you mean by omega regular expressions?
It's essentially you replace the star with a little omega, which means that you can repeat infinitely many times a pattern.
Yes, the system would be extensible to that. Now, but is the theory of omega regular expressions decidable?
Yes, it very much is.
So as long as you have a calculus of proof rules for expressing proofs about those omega regular expressions, then you would be able to encode those kinds of proofs in zero knowledge.
Cool.
Similar question. If you had considered or looked at regular tree expressions at all, it would be very useful for like XML validation in a zero knowledge way.
Yes, the answer to that is similar. That you would need to make your own theory of proof rules for expressing the certificates.
Sure.
Well, that, as far as I'm aware, that doesn't exist currently. But if it would be possible to create that theory, so then you could do it in zero knowledge.
Thank you.
Well, thank you again.